All right. Like this impulse is actually sounds like a cheap perfume sold at CVS, right? That's why I say it 3 times. Impulse, impulse, impulse. I've been using that joke for 25 years, and guess what? 2 years ago, someone actually found impulse spray and bought it for me, and I have it somewhere in this room. It's amazing. They actually do have it. It's amazing. If I find it next time, I'll share it with you. Okay. So when you say impulse, we already know this concept. Now, this impulse, when you see this word impulse, replace it with change in momentum. Okay? Because that's what really is. It's just change in momentum. Now, this change in momentum using Newton's second law, right, F equals ma, can be changed into force times time. So here, impulse is represented with capital J, okay, because I is taken by current. Right? So impulse is a language used, right? So say J, okay, is equal to change in momentum, right? Now, this change in momentum has to happen in very small time frame, okay? Uh, so delta t must be very, very small, right? That's when we define collision, okay? So when force happens during that little small time, okay, that's when collisions are defined, okay? So impulse is a language used and the variable used for delta p, change in momentum. So instead of calling it change in momentum, they just call that an impulse. When dealing with collision and explosions, okay, when delta p happens in an instant or very small frame of time, delta t is really, really small and it makes the force very, very big. Okay? Now, if you were to take a look at Newton's second law of motion, F equals ma, last chapter we actually defined the sum of all forces equal to delta p over delta t. This delta p over delta t, okay, pretty much is basically net external force. But when we talk about collisions, the force of impact, right, or the collision, the force generated by the collision, okay, is also can be defined as impulse divided by time. That time, delta t, is the time during collision, okay? So impulse divided by delta t. This is definitely not zero, right? This delta t is very, very small, right? Okay? So, if you think about it, delta P can also be represented as force times delta T. Okay? So that's also impulse. because this is impulse and that's impulsive. So if you multiply both sides by delta t, this delta t will cancel out, but this will be force times delta t. Okay? So note, when we choose to do this, we go away from two-object system approach, right? For example, in a two-car collision, we now use the force on one car as external force on the other car, and by looking at the change in momentum of an individual car, we will calculate the force of the collision. This is a departure from center of mass analysis of two-car systems, okay? So we're going to treat them individually. Remember, what is in and what is out of the system is arbitrary. That's up to you, how big you want the system to be. Is it inclusive of these two cars, or is it one each, right? And we will go back to two-car systems and conservation momentum as well. So we'll do both, okay? And if we were to take a look at graph of force versus delta t, right? So since change in momentum, which is impulse, is equal to force times delta t, this force versus time, the area underneath here is my impulse, delta p. Now don't forget, this is force versus time, right? So here, this is t initial, and this is t final. So this becomes my delta t, okay? So the area represents, okay? If you remember, force versus displacement or position, right? This is my x initial and this is my x final. This was work, right? So you got to watch what your axis represent, right? This is work, or this is impulse, okay? So this is force versus t, and this is force versus position. Okay? So don't get these two mixed up. Okay? Don't get these two mixed up. Where this is actually a dot product of a force and displacement vector, where this is just a product of force times time, delta t, to get impulse. All right? All right. So what is impulse? Well, anytime a force appears very quickly and disappears very quickly, that force can be categorized as impulse force. Okay, so that's very important to know. The impulse force is a big giant spike that happens. Okay, and the spike is kind of hard to figure out the actual function of that, but I'm sure you could probably get it. Okay, and the change in momentum that comes from that is called impulse. Okay. Therefore, these sharp spike type function in math are called delta functions. And if you were to take a look at this area right here, and then compare that area with this area here, it's basically average force between those two time intervals. Okay? So I don't know if you guys remember from your calculus class. So this is the mean value theorem, right? Right? Says force average must exist, right? At such that, right? Area, right? Under F average, right? Is equal to area of spike, right? Okay. So when we are actually talking about the force, impulse force, we could also be talking about the average force that happens between the same two time intervals. Okay, it's the average force. So the maximum force may be way up there, but we're looking at just the average force between those two time frames. All right, so here's a simple example of an impulse problem. Okay, let's say a pitched 140-gram baseball in a horizontal flight, right, with initial velocity of positive 39 meters per second exet is struck by a batter with a bat, right? After leaving the bat, the ball travels in the opposite direction. So here, your initial velocity is equal to positive 39 meters per second exet. Your final velocity after the collision, Vf, is equal to negative 39 meters per second exet. Right? The impact time, right? The mass of the ball, I guess, is 0.14 kilograms. Okay? The impact time is 1.2 milliseconds. This right here is my delta t. So what impulse acts on the ball? So for part A, right, J impulse is equal to change in momentum, really. And change in momentum is really nothing more than momentum final minus the momentum initial. Momentum final is MVF minus momentum initial, MVI. Well, the mass of the ball is 0.14 kilograms. VF is actually negative 39 meters per second minus 0.14 again times positive 39 meters per second. You must put your directions in for your velocities. Okay, you must do that. Therefore, this becomes negative, right? This is negative 5.46 minus 5.46. So your change in momentum or impulse comes out to negative 10.92 kilograms meters per second exet is your change in momentum. Okay? Now they're asking for part B, what is the average force acting on the ball, right? So for part B, right? Force average is equal to delta P over delta T. Since we know delta P, which is negative 10.92, right? Divide that by delta T, which is 1.2 times 10 to the negative third seconds. This is kilograms meters per second. So that is equal to, right, negative 9,100 newtons exerted. So the force was given to the ball in the negative x direction, 9,100 newtons. That is actually quite a significant amount of force, if you think about it. All right? Because average human being would weigh about 600 to 700 newtons. If it's 9,000 newtons, that's like quite a lot, you know, 12 to 13 times the weight of the average human being. So, in order to really change that ball, its momentum coming in and making it go out in the opposite direction with the same amount of momentum, you're going to have to apply some serious amount of force. That's why those Major League Baseball players get paid a lot. Or they juice up a lot. I don't know. Right? All right. So what about repetitive series of collisions? Okay. A machine gun fires R number of bullets per second. Okay. So this R is like the rate of fire. Okay. So let's think about this. R is a rate of fire. Or number of bullets, right, per second. Or number over time t. Okay? Each bullet has mass m and speed v. So since we're firing in the positive x direction, I guess our velocity is positive v exit, right? The bullets strike the fixed target where they stop. So basically, it hits the target and just falls right down. Okay. What is the average force exerted on a target over a time that is long compared with the time between the bullets? Okay. Well, let's take a look. So force on target, right, by bullet, right, must equal to, okay, force on bullets, right, by target, right? So this is, action reaction pair, okay? If you want to think of it that way. Action reaction pair. Okay? So if you think about the force on target by bullet is one bullet is delta P of the bullet divided by delta T, really, right? But if there are going to be n amount of bullets being fired, okay, if there's n amount of bullets being fired here, you just multiply by that number of bullets. Well, we know that n over delta T, this right here, is our R, right? R, right? Remember, R is equal to N over T. So R times delta P is equal to my force. Therefore, my R times mv final minus dmv initial well, final velocity is zero. As soon as it hits that target, right, it comes to a stop, right? So my VF is zero, so that goes away. Therefore, negative R times mv initial is pretty much, right? All right. So now obviously this negative right here is how much the force on bullet is by the target is happening, right? So it's going to the negative direction. Okay. So that this negative sign is just basically opposite of the bullets. All right. So since this negative tells you the direction that target has to exert onto the bullet. Okay. All right. Any questions? So if you want to, you could say R M V I Exerted. All right. So if you want just a force on target by the bullet, it's just positive value. All right. All right. So how does collision and momentum work out? Well, we will now return to the two-body system approach and consider all collisions from the perspective of no external force effects on the collision action-reaction, right? So the force on 1 by 2 is equal to force on 2 by 1. The approximation that all external forces are negligible during the short time of the collision is very good, okay? So it's very important that we understand no external force affecting the collision. Right? external forces are negligible. Okay? Therefore, for all collisions, F external is equal to 0. This is the only reason why the momentum is conserved. Okay? Because of this, according to Newton's third law, right? Since the net external force is equal to change in momentum over change in time, if this is 0, then this must equal to also 0. That's why delta P must also equal to 0. Okay? Which means momentum final minus the momentum initial must equal to 0. So if I bring this negative initial momentum to the other side of the equal sign, I get initial momentum is equal to final momentum. Okay? So if there are more than one object, then there are more than one momenta, right? So I'm going to put sum of all initial momentum must equal to sum of all final momentum. Okay? So this must hold true as long as there's no external force acting on the system. So you must remember this. Kiss is just a kiss. Sigh is just a sigh. Fundamental things apply. Goes by. All right, so this is very important. Sum of all initial momentum must equal to sum of all final momentum for all collisions where net external force is equal to 0. All right, so categories of collisions. There are elastic and inelastic collisions. Okay? Elastic collision, they will bounce off each other. Matter of fact, they don't even touch. This is probably like the most, perfect collisions you could get in the world. It mostly happens in a atomic level or even subatomic level. Okay? So you could consider this elastic collision world's best collision, right? And the reason why is all the initial kinetic energy it possessed before the collision is completely conserved, and you end up with the same amount of kinetic energy. Matter of fact, when you have like two, I don't know, atoms come by close together, right? Because of the electron clouds, they don't even touch. They like come in and bounce out, you know? And when that happens, all the kinetic energy is conserved. But there's no like heat generated from the collision. Okay? So important thing about elastic collision is, right? All of the kinetic energy before the collision, right, is recovered after the collision. Therefore, total sum of all kinetic energy before the collision for all the objects involved is equal to sum of all kinetic energies after the collision. Now remember, kinetic energy or work or any energy doesn't have any direction. So these are all scalar quantities you add up. Whatever the energy each object has, add them up before the collision, and then add up all the kinetic energies after the collision. Okay. Well, for inelastic collision, right, this is mostly the human scale, what's happening in our real world, right? So this is the realistic collision that we witness in human scale. So usually the kinetic energy is transferred to some form of other energy like heat energy or sound energy, right? Some sparks can happen, light energy, right? And other mangled type of, materials that you'll get. Now here's the important thing. Therefore, the kinetic energy is not conserved before and after the collision in this case. Okay? So if the kinetic energy before the collision and after the collision are compared and they're not equal to each other, that means it is inelastic collision. Now third type will be completely inelastic, right? And this one is when they stick together. When like two bodies come in, they collide and they become one, right? Objects stick together as one after the collision. Now, opposite of completely inelastic collision will be explosion. Because now the object started as one body, and then they become many bodies. So opposite of completely inelastic collision will be explosion. Okay? All right. All right. So here's some example problems that we need to know how to solve. Okay. So we're given a situation here where a 5 kilogram particle moves in the positive x direction with a velocity of 6 meters per second, shown in the figure below. So here, this is the initial condition, okay? And this here is the final condition, okay? So, initially, I only have mass 1, which is 5 kilograms, traveling at initial velocity 1 of 6 meters per second, exet. Two-kilogram particle is initially at rest. So here, this one has V initial 2 is equal to 0 meters per second. Okay. Now, V final for mass 2 is 5 meters per second. But we don't know exactly what angle that this thing is shooting off. Oh, we do know, 30 degrees. This is good to know. This is theta 2. Theta 1, we don't know. And we also don't know how fast it's moving. We don't know the V1 final. Okay? Well, V1 final will have its components of V1 final x, which is V1 final cosine of theta 1, right? And it will also have V1 final y, right? Which is equal to V1 final sine of theta 1. But don't forget that this is going to be negative direction, right? So I would put a little negative sign in here just so, because we're using the reference angle of theta 1 to be in the fourth quadrant, okay? All right. So momentum will be conserved both in the x and y direction. So if you were to look at the momentum of this, right, so this will also have VF2x, right, which is equal to VF2 cosine of 30 degrees. And then we'll have VFY, right, VF2y, which is VF2 sine of 30 degrees. Okay. Now, if we multiply these by mass of 2 kilograms and 2 kilograms here, this would become a momentum in the y direction and momentum in the x direction. Okay, so we can actually say, right, momentum final 2 in the y is equal to M2 VF2 sine of 30 degrees as well. Right? And similarly, right, momentum final 2x will be m2v2 final cosine of 30 degrees. So momentum will be the same thing. Momentum here, momentum final for mass 2 is 10 times, well, 2 times 5, which is 10 kilograms times meters per second. So we could pretty much figure out a lot of stuff, right? All right, so let's think about breaking this thing up into its x and y components, okay? Into x and y components. So let's figure out all the x's on this side and figure out the y's on this side by breaking it up into two columns. Is that okay? All right. So let's take a look at x first. I should use different color than purple. We'll use x on this side. I use purple on the y side here. So here I can say now sum of all momentum initial in the x direction must equal to sum of all momentum final in the x direction. And in the y direction, right? In the y direction, we could say sum of all momentum initial in y direction must equal to sum of all momentum final in the y direction. All right? Let's do the x's first. Here I have m1 v1 initial in the x plus m2 v2 initial in x must equal to m1 v1 final in the x plus m2 v2 final in the x. Well, what's my m1? M1 is 5 kilograms times V1 initial is 6 meters per second plus M2, which is 2 kilograms times initial velocity for 2 is 0. That is equal to M1, which is again 5, times V1 final in the x direction is really nothing more than V1 final cosine of theta 1. Plus M2, which is 2 kilograms, times V2 final x is really nothing more than 5 times, right, cosine of 30 degrees. Right? Because this here is 5 times cosine of 30 degrees. So if you work this thing out, here you're going to get 30 is equal to, right? 30 is equal to 5 times V1 final times, what's cosine of theta 1, which we don't know, plus this would be 8.66. Okay? So here, we're going to have two unknowns, V1 final and theta 1. We don't know these two. So let's solve for this. Let's see what we get. So if we solve for V1 final, cosine of theta 1 is equal to 30 minus this, right? 30 minus 8.66, right? Divide that by 5, right? And I get something like 4.268 is what I get for my V1 final cosine theta 1. Okay, so this is one equation we have with two unknowns. Now let's take a look at y's. In the y direction, here I have nothing is going in the y direction, in the initial, because this one's going in the x direction. This is at rest. So initial momentum in the y direction is 0. But if you still want to write this down, you can. M1 V1 initial y plus M2 V2 initial y is equal to, right, M1 V1 final y plus M2 V2 final y. This is 0, this is 0. So initially, I have 0 in the y direction. All right? Therefore, if I plug in these values, M1, which is, we don't know, right? We don't know what M1 is. Well, we do know what M1 is, but we don't know what V1 final y is. So this is 5 times V1 final is negative V1 final sine of theta 1, right? Plus M2 is 2, right? M2 is 2 times V2 final, which is equal to 5 times sine of 30 degrees, and that is 2.5. So this is 2.5. So here, if I bring this to the other side, it becomes negative 5. Divide that by negative 5 times V1 final sine of theta 1. So my V1 final, so if I divide both sides by negative 5, I get 1 is equal to V1 final sine of theta 1. So I have a second equation here. So if I solve for V1 final here, V1 final is equal to 4.268 divided by cosine theta 1, and substitute this into my V1 final here, I get 1 is equal to 4.268 over cosine theta 1 times sine of theta 1. This sine over cosine is tangent, So it's 4.268 tan theta 1. Therefore, if I solve for my theta is equal to, my theta 1 is equal to tan inverse of 1 over 4.268, which is equal to, hey,
where are you in terms of AP1? What are you doing?
we're testing chapter 10 tomorrow. 13.2 degrees. I got 13.2 degrees for my theta 1. Now, of course, we already gave negative angle to this already, so we know it's going to be a fourth quadrant. Okay? So, all right. So once we know this, now we can figure out V1 final for either way. You could put it in here, or you can put it in here. All right? So what do we do? Well, where do you want to put it? Let's put it in here. Let's see what happens. Right? So if we put this back in here, right, my V1 final is, so 1 divided by sine of, right, the answer here. And I get 4 point, so my V1 final is equal to 1 over sine of 13.2 degrees. And I get something like 4.38 meters per second as my V1 final. Okay. So what does that tell us? Well, it tells us a lot. Is this collision elastic or inelastic? Well, first of all, let's find out how much kinetic energy it had before the collision. What's the total kinetic energy initial? It is 1 half m1 v1 initial squared plus 1 half m2 v2 initial squared. Here, 1 half times initial, well, mass 1 is 5 kilograms. Initial velocity was 6, and 6 squared, right, plus 1 half times 2 times 0 squared. So what I get here is, I get 36 times 2.5, and I get 90 joules. Well, what about the total kinetic energy after the collision, right? 1 half m1 v1 final squared plus 1 half m2 v2 final squared, and I get 1 half times 5 times v1 final is 4.38 squared. We just calculated that. Plus 1 half times 2 times 5 squared. So this is 25, and this is something like, I don't know. If you work it out, I think you get 73.04 joules. So, did we lose energy? Yeah. So there's kinetic energy is not conserved, right? So since, right, kinetic energy is not conserved, right, it is an inelastic collision. Okay. how much energy did it lose? Well, we could figure that out. We could say 90, right, minus 73.04 divided by 90 times 100% gives you approximately 18.8% loss. Okay? Is that good? Yeah. So you have to check to see what kind of collision it is. So the best thing to do is assume that it is inelastic collision to start out the problem. So don't, unless they tell you that it is perfectly elastic collision, do not assume it to be elastic collision. It's better to assume it inelastic first and to see if they have kinetic energies that are equal to each other before and after collision. All right. Now let's talk about completely inelastic collision. Right? We talked about this. It's a third collision, right? The third collision, which is completely inelastic, and that's when bodies stick together and become one. Okay. So, in completely inelastic, simply means objects stick together after the collision. Okay. As always, momentum is conserved in all collisions. In completely inelastic collision, kinetic energy is also not conserved. But completely inelastic collision does not mean final kinetic energy is zero, because they could actually move together as one. But they will actually have still kinetic energy. Now, the ballistic pendulum is the way they used to calculate the muzzle velocity of the guns back in the old days before electronic timing devices. Okay, so they were able to calculate how fast the bullet was coming out of the muzzle of the gun before it hit the target. You know, so a large wooden block of mass, big capital M, of 5.4 kilograms is hung from a cord. The length of a string is 0.75 meters. Right? So this is the length of the string right here. So I guess you could say length is from here. Okay. And this is also the same length, basically, because it's the radius of the arc. Right? All right. A bullet's mass of 0.0095 kilograms is fired into the block. So this mass is very small mass compared to this one. Right? So this mass is equal to 5.4 kilograms. And this mass here is 0.0095 kilograms. This mass here is combined mass, right? Because this is mass right here, small mass. So this here is mass plus mass, which is right, 5.4095 kilograms. Okay, so here is position A, and this is position B. Okay, it actually gains height from here after the bullet gets embedded into the block. It gains a height of h. So this is H. So obviously you can see that kinetic energy after the collision turns into potential energy gravitation, right? Okay. This H is, if you were to look at this right here, this here is L cosine theta, this length right here. So H is equal to L minus L cosine theta. Okay? They measured this angle here to be 30 degrees. That's what the problem says. Right? So we can figure out what the H is. It is 0.75 minus, right, 0.75 cosine of 30. So what is that, John? So 0.75 minus 0.75 cosine of 30. I get 0.1. So the height comes out to 0.10. But it's actually just 0.1. 0.1 is good enough. So that's good to know. So let's calculate what is the initial velocity of this bullet. So what is the initial velocity of the bullet? So we should actually think about conservation of momentum during the collision. After the collision, we have to think about conservation of energy. Right before the collision, this thing is moving, and this is the only thing that's moving. When the bullet gets embedded inside, it is going to be moving together as one. So the conservation of momentum must occur during collision. And we need to find out how fast this thing is moving together after the bullet gets embedded. Then it has kinetic energy. This kinetic energy will convert into potential energy gravitation when this thing reaches the maximum swing and it stops instantaneously before it swings back down again. So now, if we were to work backwards, this potential energy gravitation of the bullet block system must equal to the kinetic energy of the bullet block system after the collision, right? Then that kinetic energy, we can figure out the velocity of the bullet block system after the collision. Then we can use that as our final velocity of the mass of the two masses for the collision part to figure out what the initial velocity of the bullet is before the collision. All right? All right. All right. So we know for the collision part, right? So I'm going to consider this here to be phase 1. And the swing part right here to be phase 2, right? So for phase 1, right, the collision part, the total initial momentum must equal to total final momentum. Initially, I only have the mass of the bullet traveling with V naught. This big M is not even moving. And after the collision, I have M plus M times VF. This VF is, right, bullet plus the block. But this must come from the swing part after the collision. So I'm going to say total mechanical energy initial must equal to total mechanical energy final, because there's no work done by friction here. So the kinetic energy at A plus the potential energy at A must equal to the kinetic energy at B plus the potential energy at B. Oops, sorry. So kinetic energy at point A is 1/2 M plus M V final bullet plus the wooden block squared. This and this are the same, right? Same velocities. Plus, potential energy is 0. Kinetic energy at B is 0. Only thing we have is M plus M G H. Notice how we can cancel out the masses and solve for my VF bullet plus wooden block. All right, so here my VF of bullet plus wooden block is equal to square root of 2GH. Okay? Therefore, square root of 2 times 9.8 times 0.1. Okay? So what is that, John? So 2 times 9.8 times 0.1. And you have to square root that sucker. I get 1.4. Right? So my VF bullet plus the wooden block after the collision comes out to 1.4 meters per second. All right? Therefore, if I put this into here, I can't find my V naught. So here, now let's complete this. So 0.0095 times V naught is equal to, here I have 5.4095 times 1.4, right? So 1.4 times 5.4095, divide that by 0.0095, and I get my V naught to be 797.2 meters per second. That bullet was traveling twice the speed of sound. It was traveling Mach 2. That's a fast bullet. So if you ever get hit by that one, yeah, you wouldn't even hear the bang. Like you would feel the bullet, then you would hear the bang afterwards. Pretty sick and morbid, I say. All right, so I'm gonna stop the lecture here for today, and we can start some homework problems. You should be able to do a lot of homework problems. All right, so work on your homework problems. Let me see. I'll stop the lecture.